Hello, Chemistry 30, and welcome to your lesson on predicting redox reactions. What this is figuring out what reaction will take place when I mix stuff together by using the reduction half reaction table and figuring out if that reaction will actually be spontaneous. So this allows us to predict the reaction's products and whether it will be spontaneous or not. So, the objective we're getting through today is write and balance equations for redox reactions in acidic and neutral solutions by using half reaction equations obtained from a standard reduction table. So, first step of doing this, what's going to happen here is you're going to be given basically a description of a reaction. In fact, what I'm going to do is I'm going to skip ahead to show you a question so that there's some context for going through these steps. So bear with me here. Here we go. All right. A solution of potassium permanganate is slowly poured into an acidic iron 2 sulfate solution. So this would be an example of a problem. I have chemicals that are being mixed together, and I'm trying to predict what will the products be based on the information I have. So the first step in dealing with this is to list all of the entities that are present. You learned how to do major entities back in Chemistry 20. It's one of the main things that actually carries forward to Chemistry 30. So if you were good at that in Chem 20, well, that's fantastic. You're going to be in a good spot here. The first thing that you're going to do is figure out for each chemical, what type of chemical is it? So if it's a base or ionic, and really I mean like it's ionic, you're going to check the solubility table and you're going to see if it dissolves. So the first question you might be asking yourself, if you don't remember grade 9 or grade 10 or Chem 20, is how do I know something's ionic? Well, it has a metal in it or it has ammonium. Yeah? If it has either one of those things as the first thing in the formula, you know it's an ionic compound. In which case, you're going to look at your solubility table and see if it is soluble or not. If it is soluble, if it does dissolve, it's going to dissociate into the two ions it's made of. So for example, let's say I have sodium oxide and I want to figure out, does that dissolve? Well, I look and it turns out that everything group 1, sodium is in group 1, dissolves. So that means that as major entities, I would have Na positive aqueous, and I would have O2 minus aqueous. So I would have those two ions in solution that can now be a part of the reaction. So that's ionic. Check your solubility table. For an acid, if it is a strong acid, which means that it's above hydronium on the table, it is going to ionize into H positive and the anion it's with. So going forward to this slide right here, this is your acid-base table. It's on page 8 and 9. I'm kind of blanking on that, but it's in your data booklet. If it's above the gray hydronium line, here's hydronium, yeah, gray. If it's above the gray hydronium line, that means it's a strong acid. If it's below, it's weak. So we have a different rule of what happens for strong versus weak. If I have a strong acid, it's going to ionize into H positive in the anion. So a great example is HCl. If I have hydrochloric acid, I actually don't have HCl's together. Instead, what I have is H positive aqueous as an entity and Cl minus aqueous as an entity. Compare that to HF. Yeah, and HF, if I actually take a look at that hydrofluoric acid, it's weak. So it stays together, it stays intact, so it would be HF aqueous. I don't have separate hydrogen ions and fluoride ions. It is still together, but in solution, so it's aqueous. Molecular is easier. For molecular, as long as it's not one of these ones on the list down below, it's going to stay exactly as it was. The state doesn't change or anything. It just is what it was. Now, if it is one of these ones from the list below, it turns aqueous. It still is together. It doesn't dissociate, doesn't ionize. It stays intact, okay, and it's aqueous. The main one that you're going to see from this list is probably hydrogen peroxide, H2O2. That one comes up quite a bit in redox. The rest of these we don't actually see very often. But again, if it's one of these, right, it basically ends up turning aqueous. Elements, they don't do anything. They just keep the original state that you have from the periodic table. That's it. The only one is maybe there's a few halogens like chlorine dissolves a bit and turns aqueous. But besides that, it just is the original state that you had. So that's our first step, is to list the major entities. I want to make a quick little summary table here of this so you can kind of see what I mean by all of it. So let me just kind of move forward here, make a new page. Nope, that didn't do that. Wait for it. New page. No. What am I doing? I am not getting a new page right now. There it is. I found the button. I screwed up my buttons. Okay, so when I have ionic, the question you're asking yourself, is it soluble, right? Does it dissolve? If the answer to that is yes, then it dissociates into ions. Okay, so it dissociates. I don't know if you can hear my kids, but they're fighting right now over probably Pokemon. If it's a no, then it stays solid and intact. So stays intact and solid. Let's put underneath this aqueous ions, just so you know. And it's always going to be 2 ions that it's going to break up into. All right, so that's ionic. If I have an acid, the question you're asking yourself is it strong? Is it strong? And if that's a yes, it's strong, then it's going to be H positive aqueous and anion minus aqueous. It's going to ionize into those 2 ions. If the answer is no, it stays intact, but aqueous. So it doesn't break apart. All right, then I've got my molecular. And molecular, you're asking yourself, is it a part of the list? Is it a part of the list? If the answer is yes it is, then it will turn aqueous, but it stays intact. If the answer is no, then it's a no change. Nothing is happening. And then element is the element. Nothing happens. Okay, it just stays exactly how it was. So hopefully that helps as kind of a summary thing. That's our first step, is figuring out the major entities. So now that we have that, the next thing you're going to do is you're going to find the strongest oxidizing agent. That's what SOA means here, okay, is strongest oxidizing agent. Now, hopefully you remember that when I look at my redox table, the oxidizing agents are on the left, right, because they get reduced. So on the left-hand side, I have all of my OAs. The top of my OA table, the redox table, is the strongest oxidizing agent. And then at the bottom right, I have the strongest reducing agent. So what you're going to do is you're going to start at the very top left of your redox table, and you're going to work your way down until you find everything that is there on the left-hand side of the reduction half reaction table. So in your major entities list that you've made, you're going through your redox table trying to actually find your major entities, right? So you're trying to find something on that list of like, hey, I've got all that stuff. And then that is labeled as your strongest oxidizing agent, and that makes up your reduction half reaction. You do the same for the SRA, so that's the strongest reducing agent. So strongest reducing agent, we're doing the exact same thing. We're starting at, oh, that's messy, starting at the bottom right, and I'm working my way up until I find something that I have in my major entities. Now, I mean, this will all make sense once we're going through examples. Yes, I just want to quickly go through these steps first. Now what you do is just like you always did for a net. We've gone through net reactions before. You balance electrons in the 2 half reactions that you have. So you write out the reduction, you just write it out, yeah? For the oxidation, when you write down the half reaction, you're writing down the reverse because you're writing it down as an oxidation, right? So that means you have to write it from right to left to show it as an oxidation. Balance the electrons, the reduction, the oxidation before you combine it to make out a net. And then you cancel out any stuff that you need to, including electrons. Electrons go away because you balance them between the oxidation and the reduction. Finally, you're going to determine if the reaction is spontaneous or non-spontaneous, and you know that based on where the OA is compared to the RA, right? So if the OA is above the RA, then that means it's spontaneous. Hooray! Because it's downhill. If the OA is below the RA, so if this is my OA and this is my RA, and it's below, then this is non-spontaneous. So it does not happen. And then we would write that down. We would make sure that we note that. Okay, that's a lot. Now, going through examples is where this is going to make sense. So here we go. A solution of potassium permanganate is slowly poured into an acidified iron 2 sulfate solution. So potassium permanganate, I would look at my solubility table, and I don't actually have it on slides here, so you're going to have to look yourself and kind of trust me. But potassium is group 1, and every single thing that's group 1 actually dissolves. So potassium permanganate means that I'm going to have K positive aqueous because it dissolves and dissociates, and I have MnO4 minus aqueous. So I have those two entities from my potassium permanganate. It is slowly poured into an acidified, ooh, that's a fun word, acidified. That means that I've got acid. So I have H positive aqueous, which is how I'm denoting that I've got an acidic solution. I know that I now have that available to me. And then I have iron 2 sulfate solution. It actually tells me it's solution. I don't need to look it up because it says solution, so that's handy. Fe2 positive aqueous. And then sulfate is SO4 2 minus aqueous. There's one thing missing. Oh, do you know what it is? If you remember your Chem 20, you will. Water! Because I have solution, I know that I also have water as well. I've always got water. So these are the major entities that I have. Now what I do is I take a look at my reduction half reaction table. Here it is in all of its glory. And I start at the top left, and I'm trying to find, and I'm kind of going before the plus electrons here, so imagine a line. I'm trying to find where the first place is going down, where I have all of the chemicals on the left-hand side. So like, ooh, do I have F2? No, I do not. Do I have PbO2 solid and SO4 2 minus and 4H positive? I have SO4 2 minus. I have H positive. Got those two things. But I do not have PbO2 solid, so I don't have that full OA. But look here. I do have this. MnO4 minus plus 8H positive. I have MnO4 minus and I have H positive. I don't care about the coefficient. I just care about the chemicals. So these two things together are my strongest oxidizing agent. I'm going to label it by putting two lines here saying, hey, it's this and this together is my SOA. Super. So I figured out my SOAs. At this point, what I would do is I would actually write out this full half reaction. So I've got MnO4 minus plus, oh, there's an aqueous there. And I squished, oh, this is going downhill. But I'm not stopping. Not stopping. I've gone too far. Plus 8H positive aqueous. Oh no. Fixing it. Yeah. Okay. Plus 5 electrons. Makes Mn2 positive and 4 H2Os. Mn2 positive aqueous and 4 H2Os liquid. Okay, got that. Got my SOA, and now I've got my reduction half reaction. Next, I'm going to go down from the bottom right. This is my strongest reducing agent right here, lithium, that I could possibly have. I don't have it, but that's the strongest I could have. So I'm starting at the bottom right, and I'm going up until I find stuff that I have. So I actually forget what I've got here. Okay, all right. So as I go up, don't have any of this stuff, keep on going, and continuing, and continuing. I got iron 2. That's probably coming up here. Yeah, oh, iron 2. Right, there it is. There's my SRA. That is the first thing that I come to that I actually have. Everything else I don't have at all in my major entities. Now you might notice, hey, I actually have further up things, like I have water, right? But I don't care, because all I care about is I just care about my strongest reducing agent, which in this case would be the iron. So now I'm going to write out this oxidation half reaction by writing this backwards. So I'm starting with Fe2 positive, and then that makes an electron in Fe3 positive. So I have Fe2 positive aqueous makes an electron and Fe3 positive aqueous. All right, so I copied that out from right to left. At this time, I noticed that because this is my SRA and this was my SOA, this is very strongly downhill. Therefore, this is a spontaneous reaction. So I'm going to note that down now, just so I remember, right, that it is spontaneous. All right, I'm ready to combine into my nets. It's net time. So I've got 5 electrons in my reduction and 1 electron in my oxidation. So I'm going to need 5 of these suckers to make that work. So I'm going to multiply this whole thing by 5 to make that ready to combine. So when I combine this into my net, what I end up having is MnO4 minus aqueous plus 8H positive aqueous plus 5 Fe2 positive aqueous makes Mn2 positive aqueous, 4 waters, and 5 Fe3 positive aqueous. Oh, just barely fit in there. At this time, it is best to check and make sure that I follow through the coefficients. So double check you are combining into a net. So I have the 5, right? That also came out to the Fe3 positive to here. Good. Now, the other way that you're going to check this is you're going to check and see if the charge equals out on both sides. That is your amazing way to check everything in redox. So if I take a look at my left-hand side, I have 1 negative, I have 8 positive, and I have 10 positive from this for a grand total of 17 positive for a charge. On the right-hand side, I've got 2 positive from my manganese ion, and I have 15 positive from my irons for a grand total of 17 positive. So hooray! It balances between the two things, and I know the slide is getting incredibly messy, but it is what it is, and I know that this is spontaneous. So I'm confident in my final answer. At the end of the day, I can erase a lot of the noise on this slide. Erasing. But at the end of the day, this is what I've got. I've got MnO4 minus aqueous permanganate ion plus 8H positive aqueous plus 5 Fe2 positive aqueous spontaneously makes Mn2 positive aqueous, 4 waters, and 5 iron 3 ions. So I am done that question. Fantastic. All right, why don't we do this one in steps together, okay? So I would like you to try out writing the major entities first, okay? Then I'll take that up, and then we'll kind of find the OA, the RA, all that. We're going to do it in little steps with pauses in between. All right, so pause it now, read this question, try to find the major entities, and write them all down. So here are the answers. Mossy zinc. Don't worry about the mossy. That's just extra flavor. I've got Zn solid is placed in a solution of hydrochloric acid. Ooh, that's a strong acid, so I actually have H positive aqueous and Cl minus aqueous because that ionizes in solution. And then I also have water, H2O liquid. Okay, those are my 4 entities. That's it. So now let's pause. You find the OAs and the RAs on your data table. And now let's take a look at the OAs and the RAs. So if I go to my slide over here, the first thing that I'm actually going to find that I have for an OA going down, 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 down is actually this one right here, 2H positive, right? That's what I have. And then when I take a look from the bottom right, trying to find my SRA, zinc is actually a pretty strong reducing agent right here. So I have H positive being my SOA, and zinc being my SRA. So the rest of this stuff doesn't actually do anything. So now I can write out my reduction F reaction. I got 2 H positive aqueous plus 2 electrons gives me H2 gas. And then I also have Zn solid. Oh, wrong slide, wrong diagram. Zn solid makes 2 electrons and Zn2 positive. So Zn solid gives Zn2 positive aqueous and 2 electrons. 2 electrons. All right. So now when I take a look at these two reactions, they're both at 2 electrons. 2 and 2. That's fantastic. They're ready to mingle to make a net. I can just add them together. Also, you'll notice that this is very downhill. That is super spontaneous. So I'm going to have 2H positive aqueous plus Zn solid makes H2 gas and Zn2 positive aqueous. A nice little easy one here, and that is indeed spontaneous. Okay. Oh, I forgot to pause in between the OA and the RA and the rest of the combining, but I feel like you guys already know how to do that, so it is what it is. Disproportionation reactions, we're going to talk about this first, then I'm going to go through a few of the questions from the workbook so you got a little bit more practice seeing solutions for this, because I think that would be helpful. Disproportionation, this is a terminology thing. This is when you have the same exact chemical being both oxidized and reduced. And it's weird. It's weird when this happens. But if you place iron 2 ions in solution, for example, iron 2 is both on the left as an OA and it's on the right as an RA. So it can act as both, which is strange. There's other multivalent ions that can do this as well, right? Think about, for example, copper 1 ion. It can actually get reduced to form solid copper, or it can get oxidized in order to make copper 2. So when you have a reaction where the same thing is both the OA and the RA, the SOA and the SRA, we call this a disproportionation reaction. And actually we can kind of show a disproportionation reaction. I'm just going to erase this right here. So if I were to look at, we'll kind of stick with the example that I had on the slide of iron 2 ion. So if I look, iron 2 ion, it's a pretty weak OA. I find it right there. And then if I want to find it on the right-hand side, I actually find it right up here. So this is non-spontaneous. Yeah, but we can make non-spontaneous reactions happen using a power supply. You're going to learn that in the next chapter. So if I were to actually write out the reaction that takes place for this, for the reduction, it would be Fe2 positive aqueous plus 2 electrons gives me Fe solid. I should stop rushing because that is looking super ugly. And then I have Fe2 positive aqueous makes an electron and Fe3 positive aqueous. So this is my reduction, my red, and this is my ox. So if I look at these two, yeah, this one right here, I have only 1 electron as opposed to 2. So I'm going to have to multiply this sucker by 2. So what I end up having then for a net, and this is where it gets weird, is I have 3 Fe2 positives. All right, because if you notice I've got times 2, so 2 plus another 1 from this one gives me 3 Fe2 positives, forms Fe solid and Fe3 positive aqueous. Now this is very much non-spontaneous, non-spont. It doesn't happen, but again, as you'll learn later, we can actually force it to happen. I messed up here. This needs to have 2, needed 2 right there. So now it works out for charge because I have 3 times 2 is 6 positive, 2 times 3 is 6 positive. But this would be a disproportionation reaction because the same thing is both oxidized and reduced. So kind of neat. All right. So that is the end of the lesson. What I would suggest you do right now is you go to your Predicting Redox Reactions worksheet and you try out the first few questions. I'm going to go through here in this video, numbers 1, 2, and 3. Okay, so that's what I'm going to quickly go through, attempt to at least. So what I would do if I were you is try them out first, then come back if you are confused when you look at the key and it's not matching to see the solutions and see where you went wrong. Question number 3 especially is actually kind of tricky. Okay, anyways, yeah, have a good rest of your day if you're not sticking around. And here's the rest of the, maybe I just make this as a separate video. I'm going to make it as a separate video. You enjoy your day. I'm saying bye. I'm pressing stop. I'm pressing record again.